Yeah, continuing from where we left off, we saw expression evaluation using the stack. And as we already said, the stack is also a list. It consists of the operations push, top, pop, and empty. It's a last in, first out list. That means you can only insert an element, insert and delete elements at one end of the list, unlike the, remember the example list that we saw, we could insert and what we mean is if the stack is something like this, you can use an array or a linked list representation, something like this, and you can only insert from, let's say this is the end at which I'm inserting, and I can only insert from here, and also I can only delete from here. Okay, let's call this the top, the stack. Okay, so that's the most important point about the stack. It's also a list. If I'm using a linked list representation, this may look something like this. What I mean by that is when I have a list like this, and what I will do is I cannot insert at the end of the list. Remember that example that we did in class. We always insert. You could either use, you can either insert from here or you can insert here. Insert it here and only access elements from that end. Okay, so you can do either of them. So this is the stack implementation. It's also a list of elements. The important point is it is also a list of elements, and it's just that the operations are restrictive on the stack. Okay, let's proceed a little bit. And what we did is I kind of sketched the algorithm for the infix to conversion of infix expressions to postfix. I'll just go over this algorithm. Let's say there's an input string that is given, which is an expression made up of characters, whatever. I'm using characters in this example. So when you see an apparent, what do? You straight away place it in the output. When an operator is read, what do? We check what is there on the top of the stack. If the top of the stack consists of an operator which has higher precedence, then you pop operators of the stack until top of stack has lower precedence. Then you stack the current operator. When you see a left bracket, what do? You stack it, put it on the stack. Then again, you repeat the same operation as you were, again, with the operators, you can follow the same precedence rules, everything after you see the left bracket, stacking the operators and unstacking them depending upon what is with the particular precedence. But finally, when you see a right bracket, because right brackets have highest priority, you pop all the operators of the stack. And then you finally pop all the elements, all the other operators of the stack, okay? Once you come to the end of the input, okay? So this is essentially what this infix to postfix expression is all about. Let me just correct this. There's a small bug in this figure. What we do is, let's say I'm drawing the stack from the bottom. So initially, let's say this is the expression that I have, A plus B star C plus D plus E slash F. So what do? I see an operand, I push it to the output over here. Then I see an operator, I put it on the stack, because it's possible that I might get another operator which has higher precedence. Then what do? I see the see an operand again, I move it to the output. Okay. Then I see a star. When I see a star, what do? I stack it. I put it on the stack. Then I see a operand again, I push it to the output. Okay. Then what do I see? I see the plus. So when I see the plus, what do I do now? I compare with the top of the stack. Multiplication has higher precedence than plus, so I pop it off the stack. And then what do? The current operator that I'm looking at is plus. Therefore, this plus should have been performed before this plus. So I pop this plus off the stack and pop and push the new plus onto the stack. Okay, so stack consists of only the plus over here. Then I get the bracket. Bracket has highest precedence. So I stack the left bracket. Then what do? I stack the operators just as before. What happens? I put the operands. So I move the operand out. D is an operand. So I move it to the output. Then I see the plus. I put the plus on top of the stack. And then I see an operator. I see an operand. I move it to the output. Then I see the slash. I put it on top of the stack. And then what has happened? I've come to the right bracket. Okay. Once I come to the right bracket, I've also come to the end of the expression. I pop all the elements from the stack in the reverse order. So I'll get A plus A, B, C star plus D, E, F slash plus, there's only till the thing here. But there should be one plus on top of the stack still. And finally, because I've come to the end of the expression, I pop the last plus from the stack. Okay, so this is essentially the algorithm for infix to postfix conversion. What is implicit in this algorithm? The fact that there's a priority that's associated. Priority is there, and there is also associativity that is there. Okay. In fact, once you convert the expression to infix to postfix, sorry, there's a plus missing here. This infix to postfix expression, for example, has implicit within it the priority of the operators. Okay. We can also make it implicit with respect to the associativity. I want you to think about it. Okay. Now let's go to the implementation of the stack. I have implemented it just for the fun of it all. You can either grow the stack from the bottom to the top or from the top to the bottom. What I have done is I have an array like this. Then what I'm doing is I'm saying when the stack is empty, I'm pointing to this position. Okay. Then when I push an element onto the stack, I'm going to decrement the stack. That's what I'm doing. Okay, I'm making the stack grow from like this. Okay, top to bottom. You can do either way if you wish. It doesn't really matter. This is just a question of convention. As I said, each person can do every which way you want because this is private implementation of your ADT. The way you define your data type and the way you operate on it is all your choice. Okay, so I maintain a pointer to the top of the stack. And I have defined the stack as a string because I'm assuming that my expression is made up of letters and numbers. And I have some operations which creates an empty stack, pushes an element onto the stack. We have defined the stack is going to hold the operators, therefore it's of type character. I can have an element type here also. Then top, pop, empty, and so on. Okay. Top will come, look at the element on the top of the stack. Pop will also look and also remove the element from the top of the stack. And empty will tell you when the stack is empty. Okay, so let's look at this again here. So make null will essentially update this pointer top of stack to stack size, saying that there's nothing on the top of the stack. So if I see top of stack equal to stack size, I can say that the stack is empty. Then what happens when I'm pushing, I decrement the stack and make, remember in C, we're going from 0 to stack size, but the elements are actually from 0 to stack size -1. Decrement the stack size. I push the element onto the stack. Top, what do? Stop, toss, like then return. If it's equal to stack size, that means it's empty. Otherwise, I return the element which is there on the top of the stack. What does pop do? It also does the same thing over here, but there's one extra operation that it does. It will return the top of the stack and also it will delete the element from the stack. Okay, and empty will tell you that whether the stack is empty or not. What is interesting is all these operations that we have talked about with respect to stack can be performed in order one time. Okay. Now, I want to show you something else. The important point is we used an array implementation and, sorry, 1 minute. I used an array implementation here and I made the stack grow from the top to the bottom. You can make the stack grow from bottom to top if you wish. Nothing prevents you from doing it. And you can also use a linked list to represent the stack. Okay, so I would encourage you, I've done the easier job of implementing using arrays. I'd like you to see how you can implement using a linked list, and also make sure that all operations are done in order one time. Now I can also use a list ADT, because we said a stack is after all a list. It's a restrictive list, you know. So what I mean by that is, we had a list, remember, which we talked about, which was like this. And you could insert anywhere, delete anywhere, whatever you wanted to do. You had access to the previous pointer if you wanted, previous element, next element, and so on. Everything you could access on the list. But what we are saying is, in the stack, there's only one end that it works from. So we can make the list which we defined earlier and use this list to define any operation that we want. Okay, use it as a stack. How do we go about using it as a stack? That's what I want to show you over here. Let me erase this. So I have a class. Let's assume that we have already defined this ADT list, and with its operations, a pointer. I'm using a linked list representation over here. I'm just, just to show you something different over here. Then I have the empty, the insertion element into the list, retrieve, print, whatever I wanted, all those operations that are there. Now, how do I use these? How do I convert this list to a stack? So here's an example. I have a class called stack. And what am I doing over here? I have, notice that as part of the data representation of the stack, I'm using a list ADT over here. Then what am I doing? I'm pop, top, push, empty, all these operations, which I was, which were defined with respect to the stack, are defined exactly as they are. But what I'm going to do is, I'm using a list here. Notice here, top, I'm L dot retrieve L dot first. Whatever is I'm keeping the header pointer as the top of the stack. Why am I doing this? Because the operations will be order one. If I did this, pop, what do? I retrieve the element at the beginning of the stack and then delete the element. Notice the difference between pop and top. Pop only retrieves the element, just like we saw in the array. And in the top only retrieves the element which is there on the top of the stack. Pop also deletes the element which is there on the top of the stack. What does push do? It inserts a new element onto the top of the stack. I'm using the front, okay, because I have a single pointer to the list over here. Make null, create an empty stack. I'm going to use the list make null. And now I can write an application. Here in main, for example, I have a stack A which is using this new stack that I have and performs the various operations on stacks from lists. Okay, so these are the important point is we can also reuse what we have already done, or we can create new ADTs if we like. Okay, so the general idea is when you have something that's compiled and working well, reuse it. Then after, try to see if you can make something that is much more efficient. Okay, so let me stop here and